Hello and welcome to this course on advanced plasticity of solid continua. Today we will go through with lecture 4 as before in two parts, and the subject of this talk will be on transport theorems, divergence theorem and balance laws. Basically these theorems that we have been talking of here, transport and divergence theorems, they only inform the balance laws during the localization. So essentially they are all related. Those of you who have a background in the mechanics of solids, in a slightly advanced form, they already know about this, but I will not assume such a background to the extent possible. Or if you have a background, then to refresh your memory, to jog your memory, this will be good. So let us go through with it. So the motivation here is to derive the balance laws from the first principles. By first principles we mean Newton's laws, right? Newton's laws of motion. Now that is a statement of equality of forces over the entire body, right? So the entire body, to represent it in a continuum framework, would require integral statements, because every term has to be an integral over the entire body, right? So these integral statements, which are applicable for the entire body, then must be converted to a local form. Now what is the meaning of this local form? It means that the integral statements are valid over the entire body, right? On the other hand, this is my entire body, let us say omega t, and I need to therefore have integrals over omega t in order to be able to write the balance of forces, right? So all the forces, dx, dy, dz equal to 0, something like that, okay? So that is the balance of forces, that is the Newton's law. On the other hand, if you are able to write this in a pointwise form, that is for every point within omega t, that is called a local form. The advantage here is that if you write the balance laws in a pointwise form, a point is a completely local representation. It does not know where the boundary is, what the body is, what is the shape, size of the body, etc., right? So therefore the local statements are far more general than the integral statements, because they apply to any body of any shape, of any size, etc., okay? And there is a second advantage which is even more beneficial. That is, the local forms are typically in the form of partial differential equations. The integral statements are not partial differential equations, they are integral equations. The mathematical tools that we have to solve and understand partial differential equations are far more well developed than understanding integral statements, right? So therefore that's an extra advantage. So these are the two basic reasons why we need localization. So for this we will be using a standard principle of localization as indicated here, but to use it we will need transport and divergence theorems, right? So therefore let us go through with these theorems first. But first let us see the basic idea here is that consider the reference body omega 0 here, okay? This is the same symbols that we have been using. And the spatial or the deformed body, also probably can be called the current body, omega t. You remember that t is the parameter which defines different spatial configurations. You can think of t as time. Then you can take any arbitrary proper subset p0 of omega 0 in the referential body. It should be a proper material subset, okay? No part of p0 should go out of omega 0. That particular p0 under the deformation map phi will be convected to the subset pt, which will be a subset of omega t, that is the spatial body, correct? We have already seen that this is true. So most of our work on the integral statements will be on such an arbitrary capital PT, okay? So capital PT is arbitrary because P0 is arbitrary. Okay, that's the reason. So let us now move on with the transport theorem first. It is also called, for historical reason, Reynolds transport theorem. So let us consider psi to be a scalar field, okay, and any P0 in omega 0, a proper subset of the material body, right. Then the derivative, so this is the integral that I am interested, and there is a dot on top, you can see here, right, this dot on top. This means that this is the integral's derivative with respect to time. So it is the same thing as saying d dt of integral pt psi dvt. Okay, dvt is a small infinitesimal volume element in the spatial body. Okay. Now, so consider this this derivative, okay, of this integral in the spatial body. Now we know the relationship between the infinitesimal volume elements dvt and dv0, as already we have seen that dvt is j dv0, where j is the determinant of the deformation gradient f. You should recall that at this stage. So, therefore, I can transform this integral into the material or the referential form in this manner as shown here. Okay. Since the boundary of this P0 is fixed, it is not changing with time, right. So, therefore, I can take the derivative with respect to time, the dot which is lying outside of this integral, as you can see here, inside. I can take it inside because P0 is fixed. It is not moving with time, right. So, therefore, I can put it inside and take the derivative of the integrand effectively and apply the standard rules of calculus to write it in this manner, because the derivative of psi j is psi dot j plus psi j dot, right. Now, we already have seen another relationship relating j dot with j, correct. So, you recall that j dot was basically equal to j dot, j is basically the determinant of the deformation gradient, j dot was j divergence of the velocity field v, you remember, okay. So, therefore, I can write this, use this to replace this j dot here and write it in a simplified form with j coming out of both the terms and as a common factor. And therefore, finally, after a simple manipulation, I get this thing. Okay. So, therefore, this is essentially the integral over pt psi dot plus psi divergence of v d capital Vt. The reason why I am using capital V to denote the infinitesimal volume elements is because of the simple fact that there is a small v which is the velocity, spatial velocity vector being here. So, when there is a scope of confusion, I actually use capital Vt to denote the infinitesimal volume elements. Okay. If there is no scope of confusion, if this small v as velocity does not appear in the expression or in the entire page, then I can use d small v itself as the spatial volume element. Okay. So, it should be clear from the context. This is exactly what the Reynolds transport theorem is. So, if you want to take the derivative, time derivative inside the integral, then you get an extra term psi divergence of v, right. So, now let us also, so you remember this. So, this we have already seen that j is the determinant of f and j dot is j of trace of the velocity gradient, which is also equal to j times divergence of v, which we have made use of in deriving Reynolds transport theorem already. Okay. You also recall that this particular fact can be derived by simply doing, the differentiation of the basic definition of the determinant of a matrix. Okay, with respect to time, you have to differentiate. So this is the identity we have used in deriving this relationship. Okay, so this is the background information if you need in deriving it. Now we are ready to first talk of the mass conservation. This is not a force balance, but balance of mass. Mass is neither destroyed nor added, or let us assume that this is the case. There is no chemical reaction so that there is no mass destroyed or added or things like that. So the global mass balance simply states that the total mass remains the same, right? Whether it is the spatial body or the material body, it doesn't matter, right? So therefore this is the statement for the global mass balance. You see the left one here is the statement in the referential form. The right and the middle one here is the statement in the spatial form, and both are 0 because mass doesn't change. Okay, so remember that rho xt here is the mass density over the spatial body, whereas rho 0x is the mass density over the material body or the undeformed or the referential body. Okay. Now on this particular integral, okay, you apply Reynolds transport theorem, that is, try to bring this derivative of time d dt inside this integral. Okay. To do that, if we use Reynolds transport, we need to replace this rho of xt by this quantity as indicated here, you recall. Okay, that was just discussed now. So therefore now comes the issue of localization. Okay, so this statement, that is this integral over pt is 0, is valid for any arbitrary choice of pt, this pt, as long as pt is a proper subset of omega t, or even if pt is the full omega t, the full spatial body, right. So this can therefore be satisfied by requiring that the instead of the so the fact that the integral itself is 0 can be satisfied, by requiring that the integrand is identically 0 for all points within pt. Okay. This is not necessary. You can still have very complicated expressions with additional terms here, which will still upon integration be evaluated to 0. But this is one way of ensuring that the integral is 0. You understand? So this is the localization principle. Okay. So this principle of localization therefore requires us that we can set this rho dot plus rho divergence of v equal to 0. Okay, that is essentially the local form of mass balance. So you see the integral statement is far more complicated here, no? But this now is a partial differential equation. It has a derivative with respect to time. It has a derivative with respect to space here in divergence of v term, etc. Okay, so this is the basic idea of coming from the global statement to a local statement. Okay. Now let us continue to talk about this mass conservation. You can write this integral, the total mass enclosed by the subset pt is integral rho dvt, and that can be written in the material form. So therefore I can say that because this j comes to relate the dv0, the material volume element, to the spatial volume element dvt, therefore I can say that this rho j must be related to the rho 0, the material form of the mass density, right. So therefore I can simply say that rho 0 is equal to rho times j, where rho here is the spatial mass density. okay, mass density written in the spatial coordinate. So now this is also another very interesting thing which is very useful again. Consider any integral over pt, okay, which involves some rho. Let us consider psi to be a scalar valued function, okay, scalar valued function. And let us say that there is a d dt, time derivative outside, okay. So if you want to take it inside as such, then you will have to apply Reynolds transport theorem, correct, because it is the spatial volume pt which is moving with time, evolving with time, right. So let us do that and apply the transport theorem, right, Reynolds transport. Apply it to both the terms rho and psi. So you will be having the total derivative d dt of rho psi, which will have two terms, rho dot psi and rho psi dot, okay, rho psi dot and rho dot psi here, you see on this side, okay. And there will be an extra term, rho psi divergence of v, correct, this. So this we have written. The point here is that if you rearrange these terms properly as we have done here, then this bracketed quantity here, right, this quantity encloses the fact it is the left hand side of the mass balance, rho dot plus rho divergence of v is 0, right, if the mass balance has to be satisfied, local form. So therefore this vanishes provided the mass balance is satisfied in the local form, and we are left with integral of pt rho psi dot dv. So you see this is so much beneficial for us. If we see a rho, you know, whenever rho is multiplying a field psi, these fields are typically called specific something, okay, either the specific energy, you know, or specific heat or something like that, okay. So you know, you just see that if rho multiplies your some other field inside the integral which is over the spatial volume, and there is a time derivative outside, you can simply bring it in with that psi dot, replace psi by psi dot, that is it, okay. So it is a very simple thing provided the mass balance is satisfied. Now we come to the divergence theorem, which is also extremely useful in deriving the local form of the force balance. So again let us consider that G be a spatial vector field, okay, that means it is written in terms of the spatial coordinates x and time. Now consider this divergence of G, its integral over pt, right, this is a volume integral, right, divergence of G integral over pt is a volume integral. So what the divergence theorem says is that this volume integral is related to the surface integral, where the surface is nothing but the bounding surface, the boundary of pt, okay, which is a proper subset of omega t, that is the spatial body at time t. So the relationship between this volume and surface integrals is what the divergence theorem says, okay, states. Specifically the surface integral is nothing but over the surface you have g dot n dA, where n is the unit outward normal to this, you know, infinitesimal area element dA, which is assumed to be oriented. Any bounding surface of this material, okay, of this, let us say this is my pt, this is my entire omega t, this is my omega t, this is a proper subset. This any bounding surface dA here, right, dA is called oriented provided you identify on it a unit outward. That means this is to be distinguished, this n is the unit outward normal which has to be distinguished from the inward normal which is directed inwards into that subset pt, okay. So these are, so oriented elements of the surface would be a very important thing here to understand, okay. So otherwise you cannot define n, the normal, properly, correct. This is one statement of divergence theorem. The other statement is that let us say that you know, there are multiple such statements possible for divergence theorem. Here are just 3, but all the statements are concerned with only one thing, that is the volume integral is related somehow to the surface integral. Okay. So let us again take psi to be the special scalar field. Then the grad of psi, now instead of the divergence of G here, which was a scalar, because G was a vector field, right. On the other hand, here grad of psi is also a vector field, because psi is a scalar field, right. So that volume integral is equal to integral over the surface psi n dA. N again is the unit normal. So if you take the gradient with respect to small x of psi, you get a vector from the scalar psi, okay. And psi, that scalar, if you multiply by the unit outward normal n to the oriented area element dA, then also you get a vector, right. So the equality makes sense, you know, you can check that this and this have similar mathematical identities, both are vectors, okay. So and a third form of the divergence theorem can be in the form of the two tensor fields, okay. So special form, let capital G be a two tensor field over the spatial domain. Then again the divergence of G. Now if you take the divergence of a tensor in, you know, in the indicial notation, let us say your three coordinates are x1, x2 and x3. So you have your coordinates written as just xi, xj, etc. Okay, I and j varying from 1 to 3, indicial notation. Then you know this tensor G can be written as the matrix Gij, correct? Or you can close it by square bracket also, okay. So therefore, you know, in the indicial notation, this divergence of G will be simply this derivative partial of Gij with respect to xj, okay. So it basically the Einstein summation convention is imposed here. It means that if there is a repeated index, in this particular case j, then we mean sum over this repeated index. So to write it in more explicitly over sum over j equal to 1 to 3, this, okay. So this is how you write the divergence of G, okay. So the divergence of G dV will be over the volume Pt will be equal to G times n. Here G is a matrix, right, matrix field. It has to be just multiplied by the vector n, which is the unit outward normal dA. So this is the relationship between the two integrals, one a volume integral, the other a surface integral, right. So you understand that, see, if G is a tensor, two tensor, the divergence of G, as you can see from here, because there is a sum over j, after you do the sum, only I remains the free index, right. So it becomes a vector. All right. So divergence of G is a vector. G is a matrix multiplied by the vector n also becomes a vector. So this kind of sanity checks should be done by you at times in order to ensure that everything is in order. Okay. So another useful identity that we often work with in mechanics of solids, especially in continuum mechanics, even in elasticity, is this. So consider G, okay, to be any vector field, and capital G is a tensor field, small g is a vector field, okay. Then G dot, typically G is the velocity vector v in our case, right. So anyway, so this integral over the surface del Pt, that is G dot small g dot capital G n dA, will be it can be written again by divergence theorem in terms of the volume integral, which is divergence of G dot G. You see, divergence of G is basically a vector, dot G makes sense, and G is a tensor. So inner product, Frobenius inner product of G with grad of G, okay. These are the two terms which has to be integrated with respect to volume Pt. So if it is a good exercise for you to try and derive it. Actually the best way to do that is to use indicial form. If you are not very comfortable in a coordinate independent representation of things, you can represent everything in terms of the indices xi, xj, etc., and then do this. This identity is extensively used. As I said, g will be replaced by velocity, and this capital G will be typically the stress. Okay. So you may actually like to prove it, as I said. Now, yeah, so here comes the first part of our this mechanics in the discussion, which has so far been studying only theorems. Okay, so first we need to define a traction vector. So call it by some script kind of a thing, script t, because there is already a t which is the time. I didn't want to mix it up. Most of these texts use this small t to denote this traction, but I have just modified it slightly. This traction script t is a function, is considered a function of the spatial coordinate, the outward normal, that means it is defined on a surface. Whenever we are talking of outward normal, there has to be an oriented surface element to which this outward normal will be the outward normal, right? So, and the time t. Okay. So, assume that there exists such a traction vector. That means what you are doing, you basically, this is your omega t, correct, and you can actually take any surface cut through this omega t, or you can do it in over a subset of it also. Okay. So, on this surface you have to treat this surface as an oriented surface. So, at every point you have to think of it to be that there is an outward normal n here, another n here, depends on the point x, okay, at which you are actually drawing the outward normal. Now, the thing is that you assume that there exists such a traction vector on any such hypothetical surface that crosses, that you think is imaginarily crossing this omega t, okay, or any subset of it, it does not matter. So, call this surface S, okay, this is a surface. So, then T should be this T, traction should be considered as the force density. Force density means force per unit area of this surface S, okay, force density exerted on this S from the material which is outside. This outside inside makes sense for an oriented surface, right. So, outside is this part, okay. From the outside, all the forces that are being exerted on this surface S is just given by the integration over the entire surface area of this S of script t, okay, that is it. So, this is basically what the surface traction vector means. In case, this is where actually the Cauchy's hypothesis is comes in, okay. This surface traction is a surface vector density, okay. So, if I want to relate it with something that comes with the volume, not on the surface but within here, okay, call that as some, again, a hypothetical quantity, stress, which is a function of small x and t, okay, and assume for the time being that if I take this x here, let us say, or here, okay, on the surface, here also there will be a sigma here or here, okay, there will be sigmas on the surface S, correct. So, if you take this sigma on the surface and then multiply this, think of sigma as a matrix field, multiply this sigma by the unit outward normal at this point, at any point on the surface S, then you get back this traction T. This is a great hypothesis by Cauchy, one of these greatest mathematicians known to the humankind. So, this is what is essentially needed to transfer all the surface information to volume, because as you see, sigma now is defined, stress is defined per unit volume like thing. It is defined at every point x within the solid omega t. It is not necessarily that you have to actually cross the omega t by a surface S and do it. Okay. So, with this, so this is essentially the idea. Okay. So, in the spatial body, this is the material, okay, this is the surface S, and we have a small surface element T is basically acting on the surface. It is not normal to the surface, normal is somewhere else. So, for example, in this dotted line, dashed line, that surface, the normal may be this way, okay, and the traction is another direction, okay. And and the orientation of the surfaces has to be remembered. So, with this we will conclude part 1 of this lecture 4, and we will take a very short breather now and come back after a short break. Thank you.